All right, so now that you understand hybridization in a really junky way, once again, didn't explain that very well. We're just trying to move through for the AP exam. Hate that, hate that, hate that. We can now talk about expanding the octet and why that works. So if we look at our periodic table, 1, 2, 3, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Remember, the third energy level has more space. It's a bigger diameter, so there's more space. So we now have more room for what we call orbitals, and these are the d orbitals. So let's look at sulfur. Let's look at phosphorus. Phosphorus, valence shell, 3s2. So we're at 3s2, 3p, 1, 2, 3. 1, 2, 3. So bump, 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 bump. But remember, those orbitals, they exist even when there's not electrons in them. They're kind of a space. There's an area for it. So we actually have 1, 2, 3, 4, 5 areas available for these future d orbitals. This is the third energy level. We got 3p and we've got 3d. So there's a future space there available. So now we look at phosphorus. And phosphorus says, oh, hey, this chlorine wants to play with me. 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 And they want to share electrons. How in the world could we get 5 bonds of phosphorus to bond with that chlorine? Well, we look back up here and we go, chlorine, 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 chlorine. Oh, well, I could put a chlorine here. Ooh. And then what could I do? I could take this electron and put it here. Ooh, there's space for it. And on top of that, we would get rid of it being an S, a P, and a D, and we would just say, oh, we now have 5 orbitals that have been hybridized, and they're all doing the exact same energy, doing the same space. In fact, they're just sitting there, and the nuclei are just, the electrons are sitting between the nuclei. And we go, oh, we have hybridized, or we've gone through hybridization. And what did we do? We took a D, an S, and 3 Ps. So we have DSP3 hybridization. Can you write SP3D? Yes, it doesn't matter. All right, so we have DSP3, it's how I learned it. DSP3 hybridization. We took a D orbital, 3 Ps, and an S, hybridized them, and now phosphorus has 5 effective pairs. 5 effective pairs. What's that gonna look like in the Vesper model? Well, if I take 5 things, 5 things around the central atom. 2D world, no, okay. So you can look at it and go, oh, look at that, that's how it is. No, absolutely not. 2D world, we wanna minimize repulsions. So what we're gonna do is we're gonna take 2 of them and we're gonna put them in the axis. So imagine this is a planet rotating. In fact, I'm gonna take a yellow guy and put it up here. We're gonna put it in the axis. So now we've got a 180-degree bond angle there. And then these 3 guys right here, these guys right here, there we go. Well, they're at 120-degree bond angles right there. So what we say is we have 3 in this equatorial plane, the equator, this equatorial plane at 120-degree bond angle. Can you see that? And we've got 2 guys in this axial line. They're at 180-degree bond angle. Those verbs you don't need to know. Those descriptions, they don't need to know. I don't even know if they're official. It's what I've always learned. And so now what we have is we've got ourselves a shape where everything is as far apart from each other as possible. What do we actually have? We have 1, 2, 3-sided pyramid on top, 3-sided pyramid on the bottom. That is a trigonal bi to pyramidal shape. That's this trigonal bipyramidal shape. 3-sided pyramid on top, 3-sided pyramid on the bottom. What happens if we replace one of them with a lone pair? So we'll make shapes, done this a lot, shapes, and one of them's gonna be a lone pair. Well, now let me go ahead and put one of these guys over here and one of these guys over here. I'm gonna take out one of my equatorial lines. So take out this guy right here, and what do we have? We've got a seesaw. We've got a seesaw. It's also called a distorted tetrahedron. Now, why did it take it out of the middle here? Because these are 120, where this is 180. Take out the guy with a shorter bond angle. Less repulsions, or more repulsions, so we get rid of it. And so now we have a distorted tetrahedron, or a seesaw. It's sometimes called a sawhorse too. If I have another lone pair, take out that guy right there, another guy in that equatorial line, we've got a T shape. And so I'm gonna put the yellow guys back on. Those represent lone pairs. So if you look, my shape is a trigonal bipyramidal electron geometry, but it is a T-shaped molecular geometry. If you look, it is an electron geometry trigonal bipyramidal, but it's a distorted tetrahedron or seesaw molecular geometry.